Okay, so hello everyone and welcome to the third day of the geometry workshop. Today we have with us as a speaker Dan Halperin. Professor Dan is a professor at Tel Aviv University and he is also the CTO of Assembrix, a startup in 3D industrial printing. He obtained his PhD from Tel Aviv and then he worked at Stanford as a research associate for a few years. And then he moved back to Tel Aviv as a faculty member where he established the computational geometry lab. His interests are in computational geometry and applications, including robotics, automated manufacturing, algorithmic motion planning, and 3D printing. He is also a part of the CGAL project, which stands for Computational Geometry and Algorithms Library. And this project won the Test of Time Award in SOCG 2023. He also co-authored books on arrangement in CGAL and multiple chapters in Handbook of Computational and Discrete Geometry. He has been selected as a IEEE Fellow in 2015 and ACM Fellow in 2018 for his contributions to robust geometric algorithms for robotics and motion planning. Today, he'll be talking about how geometry is used in robotics, from snapping fixtures to multi-robot coordination. Please join me in welcoming Dan.
Thank you, Kevin. Welcome, everybody. I want to thank the organizer for inviting me to this very interesting workshop with warm hospitality. It's a pleasure to be here. So I work indeed in computational geometry and robotics, and it's very natural that geometry comes up in robotics. And I want to tell you about a few things that we did. And I organized my talk in the following way. I'll start with two short segments. The first one is pretty esoteric. It's not something central to my research, but it was a creative idea by a student that led to nice geometric problems. The second brief segment is actually a very big topic in robotics, robot rearrangement by robots. I bring it here because it's very rich in geometric problems, but I only speak briefly about it. I want to focus on multi-robot motion coordination, which has been my main interest, so to speak, over the last 10 years. Now, I know that you are all theoreticians, and the first two segments will have various applied aspects, so you are welcome to ignore them, and I'll give you a riddle to think about while I'm presenting the first two segments. But please don't say anything if you see the answer now. I'll come back to it halfway through my talk. So here is the question to those of you who want to wander off. I'll explain later why it's related to assembly planning. I give you a set A of grids, of unit cubes on the unit grid. These are the gray squares here. And I ask you to find a subset S that you can slide vertically upwards without hitting the remaining squares. The remaining square A minus S. But I add another constraint, and it is that I'm asking that both S and A minus S will be edge connected. And I'm explaining. So here is a possible set S, not good. Why? It can slide upward without hitting the remaining blocks, but it leaves the remaining blocks as a disconnected set. Here is another bad example. Both S and A minus S are connected, but if I slide S upward, it will hit A minus S. And here is a good example. And I'm asking you to look at a collection of squares and to tell me how to find such a subset S. And now I move to my talk. And the first thing I'm going to talk about is fixtures. These are important elements in manufacturing because they hold a workpiece that you want to handle, to manipulate. You see here a complex fixture. But we came up with the need for fixtures, and we wanted to have very simple fixture made of one part. And we wanted to take advantage of the 3D printers that we have at the lab. So a student came with the idea that there will be a fixture that is in the shape of a palm. You put your polyhedral workpiece here, and you have a few fingers that hold it, so you can get it into the fixture. It's much easier for me to explain this with this short video, if I manage to operate it. Okay. This is video made by my students. Okay, so the first thing that we showed is that if a polyhedron can be fixtured by it, we need only 4 fingers. To find these 4 fingers, a naive algorithm would take time n to the 5, and we give an n to the 3 algorithm. I'll tell you immediately some ingredients of it. And the reason we want few fingers is either because we want the fixture to be lightweight, or I'll explain soon what happens there. You don't want it to obstruct the workpiece. You want it to expose as much of the workpiece as possible. So where is the geometry? We rely on an earlier result of us. Whenever you touch with the palm or with a part of the finger a face, you prevent it from moving in a hemisphere of directions in free space. So think of the sphere of directions, that's S2, and each constraint is a hemisphere. And what we've shown previously is that if you have a collection of hemispheres that covers the sphere, then 6 of these hemispheres are sufficient to cover it. This is a not very complex application of Helly's theorem. I guess most of you know what Helly's theorem is. If you don't know, it's good to know, even if you prefer the algorithmic side over the combinatorial sides in geometry. But even if you're not interested in the combinatorics, think of an algorithm. I give you many hemispheres. I tell you that they completely cover the sphere. And by this theorem, you know 6 of them cover the sphere. Can you efficiently find them? So you have n hemispheres. I want an algorithm better than n to the 6. And in fact, what we show is that you can find them in linear time. And the reason you can find them in linear time is a nice side effect of several linear programming algorithms in low dimensions that run in linear time. Both the deterministic algorithm of Nimrod Megiddo and the randomized algorithm by Ken Clarkson they have this nice property that when they fail to find a solution, they give you witnesses for the failure. And those witnesses are the complements of the hemisphere that we require. There are a few more subtleties in this algorithm. We don't insist that our objects will be of genus 0, but to get the efficient algorithms, we require that they have constant genus.
Does the general Helly theorem also have like near linear time workings?
What do we mean? Yeah, we have all those, there are connections between LP programs and Helly theorem. This was well researched. So I guess the answer is basically yes. We printed many of them. I have exemplars here that I can show you later if you want. We printed them in our lab printer, which is like a home printer and easily breaks, but we also printed them on industrial strength printers. And this I challenge you to break. I can give you, I mean, if you're too strong, perhaps I don't want you to do it, but it's very difficult to break them. A jeweler used our software to design an earring so that it hides as little of the diamond as possible. I also have the earrings here to show you.
Diamond too.
For this, you'll have to work harder. Now, it's going to be so practical that I want to talk a little about software. We have a software, and you can send us or use the software. You give us your workpiece, and we'll give you the instructions for your 3D printers of the fixture for the workpiece. I want to say that this type of programming is very delicate because you compute some arrangements and the answers you are looking for may lie on singular points of the arrangements. And not every software can do it, but fortunately, the computational geometry community has the SIGA library, which is actually accessible to everybody, and you can do it with the absolute precision of the SIGA library. Okay, I'm fast moving to the second topic, which I think it's most of robotics can be cast as rearranging the physical world. You use robots and you move parts from one place to another. So it's a very broad topic and I'm going to dedicate very small time to it. I bring it up here because this is currently a focus of ours and there are numerous interesting geometric problems here. So what do we want to do? We want to use robots to move from this to this. This is object rearrangement, but we start with more modest goals. We want to move these soda cans from here to here. By the way, robotics progresses very, very slowly. You should know. It's you may hear some hype here and there, but there is steady progress, but it's very, very slow. And by the way, this is not completely out of reach today. Now, you can immediately see that you need some planning here. You cannot simply move, you see where the Pepsi has to go, where the Coke has to go. You cannot simply move the Pepsi here because it's occupied by the Coke. And you need some planning. And in general, these questions have they have more, but two central components. First of all, I ignore the robots, and I'm planning a series of moves for the objects as if they move by themselves. We call it free flying. This is part one. Then you also need to coordinate the motions of the robots that carry out this transfer. Each of these problems is very hard. The first one is very famous, studied in math, in computational geometry. It's called cone problems, extended 15 puzzle, rush hour. We contributed some of our own variants related to manufacturing where you want to minimize the workbench where you do these operations. Most of the questions are hard and require some approximation. But then also multiple robot arm coordination is a hard question. Definitely if you have many robots, but even for 2 or 3 robots, when they come tightly together, the question becomes very hard. So people typically break this problem into two. They first solve this, and then plan the motions. But there is a catch, because you may have an excellent plan for the free-flying objects, but it will be very bad when you add the robots. And we decided to try and attack them simultaneously. So we have proofs for some very limited synthetic robotic systems, and for real robots, our proof that you gain something from having two robots over one is mostly by experiments. Why I wonder? I increased my workforce, but I also added complexity because the robots have to avoid one another. I'll show you another short video of a comparison between, I must learn to do this. Oh. Okay. Okay, one moment. And this is just a small experiment comparing between two robots and one robot doing the same task of rearranging the Mona Lisa. This planning of the motion is pretty complex. But the two robots win over one robot. And in order to plan the motions of the robots efficiently, we need a good algorithm with guarantees on the optimization. And we developed an algorithm called DRRT star that has the property, and this was a first of its kind for multi-robot, that it is asymptotically optimal. I'll explain this in the third and central section of my talk. What we're really interested in is reconfiguration in very tight settings. We're interested in designing the set of motions that will bring these parts together and eventually do it by robots. And that's what we are trying to do these days. And where does the question from earlier comes? So we have good polynomial time algorithms for assembly planning of free-flying objects, as long as the motion of assembly are sufficiently simple, even if they are three-dimensional parts. What do? We study the problem in reverse. We start from the full product, and we try to break it into two subsets. If we succeeded, we continue recursively with the two subsets until hopefully all the parts are separated. If this process has succeeded, and assuming the parts are rigid, we run it in reverse and we get an assembly plan. So a basic question here is, can I take my current assembly or sub-assembly and break it into two subsets and move them one away from the other? So as I said, we have good polynomial time algorithms, but this per se is insufficient because when you add a robot, you have all sorts of physical constraints. A very natural constraint is that you want your two subsets to be connected. So this, how we came up with this question, it was open for 25 years. What happens when you add this constraint? Because if you try to solve it without the connectedness, you'll immediately come up with an efficient solution. And many people, I tried to sell this problem for several years, and many people came up with efficient solutions, near linear solution, quadratic solutions. But eventually, we showed that the problem is NP-hard. It's surprising because it looks a very innocent question. We also gave an FTT algorithm where the parameter is the size of the smaller set of the two that you can move. You can either move one up or one down, and K is the size of the smaller one. We also identified some structural properties that make this question simple. Okay, so now let me move to the main part of, yes?
Sorry, could you please explain what K is again?
I look for a subset S. I can also look, I can either look for the subset S to move upward or a subset S to move downward. The smaller of the two is K. It's the size of the small subset. Okay. I should say that multi-robot motion coordination is studied by many people. Sujoy gave an example. Many people try to imitate large swarms of birds or animals in nature. But I'm looking at, so when you say multi-robot motion coordination, it's different things to different people. But I'm looking at a very, very basic variance, which is still not resolved and not completely understood. So here's the definition of the problem. I give you a system of a robot or several robots with k degrees of freedom. I will define degrees of freedom immediately. They are in a cluttered environment. It's completely known to the system. And you have to decide if B can move from start to goal without collision, and if so, to plan the motion. Without collision, if we have more than one robot, is not colliding with an environment and not colliding with other robots. So here is an example of a system. It consists of 6 robots, those L-shaped robots with full color, and each of them has a respective target. And you want to move them in this room while avoiding the gray obstacles and avoiding each other. You don't need to know robotics to understand what I'm talking about. You need to know 2 terms. One of them is the number of degrees of freedom. The number of degrees of freedom of an individual robot is the minimum number of real parameters that determine each configuration of the robot. So for this type of robot, it's 3 parameters. I can tell you the coordinates of this vertex, for example, and the angle that this edge makes with the positive axis. And when we look at many robots, we simply sum up the degrees of freedom of each robot, and this is the number of degrees of freedom of the system. So here you have 18 degrees of freedom. Here you have 10 robots with 6 degrees of each one. You have 60 degrees of freedom. Configuration space is a very nice idea that unifies many motion planning problems. You take your robot system and actually you shrink it to a point. And you study the motion of this point in a space whose dimension is the number of degrees of freedom. Because every point describes the full static position of the system. Here you see an example for a robot with 2 degrees of freedom with only translating parallel to itself. So it's equivalent to planning the motion for this point among these expanded obstacles. And most of the study of motion planning uses this notion. When the number of degrees of freedom is part of the input, the problem is known for many years to be hard. I'm not going to the specific. If you're interested in hardness classes, it's p-space hard. Some problems are NP hard, but it's computationally hard. The first general solution is by Schwartz and Sharir. It's a doubly exponential solution. The number of degrees of freedom appears in the exponent of the exponent in the running time. It's totally, people implemented it in some cases. It cannot handle anything. John Kenny came up with a single exponential solution, later worked out in detail in this encyclopedic book. We made many attempts to come up with more efficient solutions for spatial systems. What I want you to take out of this slide is that the problem is hard. And the multi-robot motion planning, because it has many degrees of freedom, is hard. And I'm going to talk about 2 types of solution. The first type is exact solutions, computational geometry style. And the second type is the more practical robotics approach, but these days it comes with proofs, unlike what happened at the beginning of this. Now, at some point I may need to skip some slides. I know it's difficult for me to ask for more time because you remember me with the bell, but I started late. So let me explain a very simple problem where we gain deeper understanding. I need to define what is K-color multi-motion planning and multi-robot motion planning. I have many robots, M robots, but they are arranged in K groups. And within each group, the robots are identical. In fact, indistinguishable. Here you have a room with 7 robots arranged in 3 groups. What do I mean indistinguishable? Suppose I tell you I want these 3 stars to be here below. I don't care which star goes to which target. So there is some freedom here. And there are extreme cases. If the number of colors is equal to the number of robots, this is the standard multi-robot motion planning, which we know to be hard. And the other extreme, and typically interesting, is there is only one color. All the robots are indistinguishable and they are the same geometrically. Here is a specific problem that I'm going to dive into, but get an idea of what is unlabeled motion planning. So I have 4 Roombas in a room. I give you their target positions, but I don't care which Roomba goes to what target position. So this is a solution, this is a solution, they are all valid solutions. And we ask the following question. I give you M interchangeable unit disk robots. They are moving inside a simple polygon with n sides. Each of the n goal position needs to be occupied by one robot, but I don't care which at the end of the motion. And I make one extra condition. When I look at all the start and target positions, where the centers of the start and target positions are, I ask that there will be 4 unit distance between them. So when I put 2 robots, they'll have 2 units separation between them, because the robots have unit radius. And this is the problem that I want to investigate. Here is an instance. You have 15 robots, 15 start green position, 15 target purple positions, and here is a verification that it holds the separation that I mentioned. I expand each robot by a halo of radius 1, by an annulus of radius 1, and I require that these expanded robots are pairwise interior disjoint. And for this, we have an algorithm with running time n log n, mn plus m squared. M is the number of robots, and S is the number of sides of the polygon. And the main questions that we asked ourselves is, how come this presumably p-space hard problem has such an efficient solution? Let me say a few details about the solution. We compute the configuration space for a single robot. So originally I have a simple polygon where I can work, but when I expand the obstacles to account for one disk, it can break into several rooms. And a robot cannot move from one room to another because this passage is too small. And the mechanism is, we first show that within each of these rooms, the problem, we give a solution within each of these rooms, and then we discuss the relation between the different rooms. Why is it relevant, the relation between rooms? Think of this room, which is distinct from this room, because the robot cannot pass here. but this robot can obstruct the motion of robots here. And what we show is, indeed, a robot in room 1 can obstruct robots in room 2, robots in room 2 can obstruct robots in room 3, but you cannot close the cycle. And this gives us a topological order for solving this problem. Now, we didn't understand what's going on here, and we try to understand how come.
One question, so if it was non-simple polygon, then you can get a simple.
No, it relies on the fact that it's a simple polygon, indeed. How come this question is solvable by efficient algorithm? And I'll quickly go with you over the different conjectures. Is it because the workspace, the polygon, is homomorphic to a disk? So we rule this out because there is an old result by Spiratis and Yap where they show that motion planning for disks inside a simple polygon is NP-hard. However, they use different radii disks. So this is a labeled version. So perhaps it's because the problem is unlabeled. And that was my belief for a long time. What I thought is, you start moving a robot towards a target, another robot blocks you. Okay, take the other robot and move it to this target. And also, it was very appealing because I thought the running time will be eventually the complexity of the room to the power of number of colors. So if it's unlabeled, it will be low polynomial time algorithm. If it's labeled, it fits with the hardest result. But my student Kirill Solovey showed that unlabeled motion planning is hard. P-space hard. Is it because the robots are simple? These are, we showed it for squares. You have reason to believe it's correct for disk, and there are now.
And is it NP-hard even in a simple polygon, or it's only because
No. This is not a simple polygon. This has holes in it. So the end result, the end of this discussion is that what makes it easy is this separation. Separation is very critical. And here is a nice question. There is a side effect if a scene, an input, fulfills the condition that I mentioned, then there's always a solution. If it fulfills the separation, there's always a solution. We asked a separation of 4, and the next question is, do you need a separation of 4? In the original paper, we showed that you cannot go below 3.6 and still always have a solution. Later, with others, we have actually shown that you cannot go below 4. 4 is a critical value. This also explains, in my view, why the proofs in the original paper are pretty complex. So it's always solvable until 4, and you cannot go infinitesimally below 4. In fact, we know a little more, and that you need to make a distinction. You need a separation of 4 between 2 start positions or 2 goal positions, but between a start and a goal position, it suffices to have a separation of 3, and you cannot go below 3. We have many variants for labeled, for some other ideas. Later on today, Pankaj will talk about optimization, but specifically about an idea called revolving areas. Okay, this completely relies on the shape of the robot being very simple in order to operate. But how do we move to these more complex robots? And this brings me to the last part of my talk, and this is how do we cope with complex shapes, many degrees of freedom. And I want to explain what is the algorithmic robotics approach to this hard problem for which we cannot supply a solution with standard low-dimensional tools in computation geometry. Even Siegel cannot cope with this. And the standard tools that are used in robotics are called sampling-based. And I'm exemplifying the simplest of them, and these are called probabilistic roadmap. So this is my configuration space, indeed in the dimension, which is the number of degrees of freedom, drawn here as 2 dimensions. These are the expanded obstacles. I don't know them, but I sample points. And each point is a configuration of the robot. Therefore, I can take the robot in this configuration, compare it with the obstacles. It's a simple intersection problem in geometry. You can have off-the-shelf software that does it. And I classify them as good point, free, and bad point, red. I throw away the red points, and now I try to connect nearby blue points by an edge. How do I connect them? I sample many points along the way, and I check if all these points are free. If they're all free, I leave a blue edge, otherwise I throw the edge. It may sound as a big bug here that I'm only sampling point, but I can be conservative here. And then I come with my start and goal configuration. I try to connect them to this graph in the same way I connect a pair of points, and then I look for a path on the graph. And these techniques dominate robotics today. I'll mention 3 main milestones. The original algorithm that I described, called PRM, a much faster algorithm called RRT. This is the most frequently used technique in robotics, and a more clever algorithm that can guarantee optimality, like shortest path, that you are converging to the shortest path. As I said, I mean, yes?
Why is it better to sample and to put a grid?
A very good question. I wait with this. If I manage ever to get to my last slide, I'll give you an answer. I think the publications, there are a few publications by the same author, by Kaffner and Laval. They are cited more than 10,000 times. I mean, in all robot systems, you have some variant of RRT. I have to explain what are the guarantees that come with these algorithms. The first one, we are used to what we call complete algorithm. Either the algorithm finds a solution, or it stops and it says there's no solution. Here it's different. This is our standard perception of an algorithm. Probabilistic completeness in robotics means that as you invest more work, you sample more, eventually you will find a solution if the solution exists. It looks very vague, but it does help to distinguish between useful algorithms and less useful. And a major breakthrough is that Karaman and Frazoli from MIT, the last item on the previous slide, came up, they looked at all these algorithms, modified them a little, and they promised something we call asymptotic optimality. If there is a solution, an asymptotically optimal algorithm will converge eventually. But it's eventually. We have no clue how much time it will take. Let me mention a few contributions by my students and colleagues to this. RRT, although it's the most used algorithm for many years, it didn't have a solid proof of probabilistic completeness. We supplied it actually there was a debate under what conditions it is complete. We supplied probabilistic completeness proof for this. The fact that RRT produces very bad results in terms of path quality, we gave a way to prove this before the big breakthrough of Karaman and Fazoli. My students, Kirill and Michal, all these algorithms rely on the radius around your sample in which you connect to other samples. They sharpen this radius, and I think the best result is by Oren Zaltzman, a student of mine. RRT is very fast. That's why it dominates, but it can produce horrible results. RRT star converges to good results, but it takes a lot of time. And Oren came up with a trick where he compromises a little for the promise of convergence to the optimality, but only very, very little, by epsilon, and you obtain the solution that runs almost as fast as RRT and produces results that are as good as RRT star. Its software is frequently used in many places. Okay, the problem with all these results, you run your algorithm, it doesn't stop, and you don't know why. Because it might be that there's no solution, and it might be that it requires more time. The theorems only predict something asymptotical. So what we obtained here is an algorithm with finite guarantees. We tell you that I give you a set of robots and two parameters, delta and epsilon. If the problem has delta clear solutions, meaning a solution where the robots are delta away from the obstacles and delta away from each other, then we have a finite sampling scheme, to answer the question, that gives you a solution. For example, if you are interested in total length of the path, that is only 1 plus epsilon longer than the optimal solution. I don't want to explain further notation here, but it relies on starting from sampling separately for each robot, and then taking the tensor product of these samples, but only implicitly. Not the tensor product is huge. We work on the tensor product very carefully. I want to tell you a small anecdote, but what we rely on is something that we call the staggered grid. What is the staggered grid in the plane? I tile the plane with same radius disks, and then I add a translated copy to cover the holes. And these are my samples. These are my deterministic samples. And I will tell you a short anecdote. Kirill gave a talk on this at the Technion, and a student told him, but this is the standard grid. He said, just rotate it by 45 degrees. It's the standard grid. It puts me in big stress. I don't mind that I didn't observe it, but we write in our paper and we give experimental evidence that in 3 and higher dimensions, the standard grid is much better than the standard grid. Okay? I eventually realized that this only happens in 2 dimensions. This phenomenon doesn't happen in 3 dimensions. The number of neighbors in the standard grid grows exponentially in the standard grid, and in the staggered grid it only grows linearly. Let me conclude. There are many approaches to multi-robot motion planning. There is the swarm distributed approach. Very interesting. I don't think there are many proofs there, but it's very interesting. There is a discrete version that is very popular when you do it on graphs, and most of the robots in warehouses work with these approaches. Machine learning has yet to prove itself in multi-robot motion planning. I don't think there is any meaningful result. The results in machine learning for this high-dimensional motion planning are not very promising. I focused on central control algorithm for continuous domains. I want to mention two areas. Assembly planning, full of interesting geometric problems, beautiful, and optimal multi-robot motion planning. I think it's something with very, very little understanding. But I leave it for Pankaj to describe later. Let me mention that Mikkel and I wrote a review of open problems in the intersection of robotics and computational geometry. It's available on the archive. I want to finish, before some thanks, with a short video. It's self-explanatory. It's part of our assembly planning efforts.
We present the first demonstration of a robotic arm solving the alpha puzzle. The alpha puzzle is a famous example for the difficulty of tight motion planning, as its solution requires non-trivial combination of translation and rotation. It was constructed by Boyce Yamron and was posted as a benchmark for tight motion planning by Nancy Amato. We note that the alpha puzzle is just one example from a family of difficult assembly tasks which require non-trivial combination of translation and rotation. We present here a partial list of algorithms that tackle that family of problems. All of them are capable of solving the alpha puzzle effectively in simulation. However, the transition from simulation to a real-world solution requires dealing with various hardships beyond the geometry of the problem. Such difficulties include finding a suitable grasp and robot placement, accounting for model inaccuracies, avoiding robot singularities, and more. And here we see a demonstration of a UR5 robotic arm solving a 3D printed version of the alpha puzzle. The solution path is very tight, as our motion planning algorithm intentionally maintains contact points between the two pieces. Our project demonstrates another step towards the automation of a full pipeline from motion planning for the free-flying objects to execution with a physical robotic arm.
I thank my students, my collaborators, my funders, and if you heard me speak in recent years, you know what these pictures are. There is an American artist. He actually has a PhD in engineering, and he's producing art by computer, and he was looking for a long time for software that can support his design, and he writes a very hearty blog how when he landed on Seagull, all his solutions were solved, and these are the pictures that you saw throughout. Thank you.
He's a professor at Georgia Institute of Technology, and he obtained his PhD at Carnegie Mellon University. After that, he joined as a faculty at MIT, where he spent for like almost 9 years. And then he moved to Georgia Tech, where he was also the founding director of Algorithms and Randomness Center. He has been named as an ACM Fellow in 2015 for his contributions to convex sets and probability distributions. And in 2022, he has also been named as a Fellow of American Mathematical Society. He won several awards such as MACT Award, the Test of Time Award at Potts Conference, and the Soda Best Paper Award in 2021. In 2024, he has been awarded with Fulkerson Prize for his work on Gaussian cooling and improved algorithm for estimating the volume of a convex body. Today, he'll be talking about sampling by algorithmic diffusion. So let's please join me in welcoming Professor Santosh.
Thank you. I tried my best to do a talk on Snap something, but because the talk before and the talk after are about Snap only, and I think I can squeeze it in, but you'll have to wait for it. Yeah. So there's one idea I want to convey here. It'll take some background, which you're welcome to ignore. So the first 10 minutes is sort of build up. Yeah. Here's the basic problem. We have a function in n-dimensional space. It's integrable and let's say non-negative, and you have some point with a non-trivial point, so the function has a lower bound, and you are given an error parameter. Your goal is to sample from the distribution whose density is proportional to f. Okay, so you have the ability to evaluate f, and you'd like to sample with density proportional to f. That's the general problem. There are lots of special cases. So, for example, the uniform distribution on any set, or on a compact set, or more general functions. The problem is intractably general, but if the set is convex, or more generally, if the function is log concave, then we have polynomial time algorithms. But the boundary of where is tractable and intractable is still not clear, just as it is in optimization. Convexity is not the limit, although it's, yeah. Okay, so that's the problem. It's a little convenient to write it like this. Now V is any function in general. We will only consider convex functions in most of the talk, right? And you have access to an evaluation article. So the uniform distribution is when V is, it could even be 0 there, and infinity otherwise. And general log concave is V is any convex function. Why do you want to study this problem? It's hard for optimization. You can do just lots of applications, such as computing the volume or the center of gravity or covariance and so on. Actually, while I won't do it here, I should mention in this application session that the fastest sampling algorithms now for polytopes or density functions where the constraint set is a polytope run in up to 1 million dimensions on your laptop even now, and you can download the code. It's on GitHub. People are using this in bioinformatics for metabolic sampling. So yeah, for various other variants of optimization such as robust and online, and the problem seems to provide some new insights into convexity and also what's computable and not. Yeah. Okay, so in this talk, I mentioned some sample algorithms and guarantees. By guarantees, I mean there are different flavors in which you can give these guarantees, and it seems to be interesting to look at the differences. And the main idea of sampling by diffusion, which is an old idea, but giving it an algorithmic flavor here, which involves moving continuous analysis to discrete complexity analysis, and then sort of a message about how the convergence of these algorithms is determined by a pure functional constant of the target distribution. Okay, so here are two of the most successful general algorithms for sampling in high dimension. So one of them is called the ball walk. It was first formulated or analyzed by Lovaas in the early 90s. And it's basically, you have a set, you're at a point in the set, so your support is the set, and you consider a ball of fixed radius delta. Delta is a parameter, pick uniformly in that ball. If the point is in the set, you go there. If not, you try again. That's it. It's the Markov chain, the ball walk. So if you do it like this, you'll reach the uniform distribution. If you instead wanted to reach some other function, you will then pick a point from the ball, go with probability which is smaller of 1 and the ratio of the proposed point to your point, the function value. That will maintain the intended target density. So here you need this parameter delta, and it's important what delta is. Of course, if I make delta large, so large that it covers the set, then one step is enough. Of course, how many? Well, one proper step. It may take you forever to make that step because the ratio of these volumes can be exponential in dimension. So the variant hit and run, first proposed by independently by Bonnet and Smith, is the following. At a current point, same state space, you pick a random direction, so a point on the unit sphere, that defines a chord, and then on the chord you go to a random point. So you do take a proper step every time, and you repeat this. Both, you'll notice, only require a membership oracle. Are you in or out? Or a function evaluation oracle. Okay, so these have been analyzed extensively over the past 25 years, and we more or less understand their limits. The way the analysis goes is by showing that the corresponding Markov chain has large conductance, which is the probability of escaping a subset given that you're in it. And this through some work is then bounded by what's called the Poincaré constant of the target distribution. I'll define this in a minute, but that's the very high level point of the analysis. And so here's what the result looks like for the ball walk. If you have m warm starting distribution, so you can't start from any point you want. I mean, you might get stuck right away. But if you start from a distribution whose density is bounded compared to the target by some m, then the number of steps to reach a target epsilon total variation distance to your target is bounded by this warmness, dimension squared. This is the operator norm, the largest eigenvalue of the covariance matrix. It certainly can be bounded by the diameter of the set times a polynomial.
Covariance matrix of the Markov.
No, covariance matrix of just the target distribution.
Okay.
Yeah, so that's right. So we're talking about something that's fixed once you know the target. Yeah, and in particular, of course, that will be this eigenvalue will be bounded by whatever is the diameter squared. Yeah. Now this proof requires additional tools, and in particular, the notion of what's called the speedy walk introduced by Kannan, Lovaas, and Shivnowitz, just for analysis, and I'll mention a little bit more about it, and rejection sampling to correct this distribution. So this bound, getting to this took 25 years, as I said, and among other things, they made the K-less conjecture, which says that this Poincaré constant of the distribution for any log concave distribution is in fact bounded by the operator norm of the covariance matrix up to a constant. Hit and run, on the other hand, the bound is n squared. R is think of it as the radius of the ball that contains the set, so r squared polylog. If for the case of uniform sampling, and more generally also, the r squared just represents the average square distance point from some point. Let's say it's centroid. The point is r squared is an upper bound on this operator norm of covariance, but it can be much smaller. So this is the state of the art. Okay. Yes.
For hit and run, we also need a warm start, or we don't need warm start?
Yeah. So good point. No, we don't need a warm start. The dependence is. Oh, I'm going in the wrong direction. The dependence is a polylog in the warmness parameter. So of course, this parameter, if you start from a single point after one step, it is exponential in dimension. So you end up paying an extra factor of n. But indeed, formally you don't need, it is polylog rather than polylog. And it's the only known walk with this property for this general set. Yeah. Okay, so in both cases, or let's go back to ball walk, we have to deal with these boundary issues. By that I just mean imagine you're in a cube and you're near the corner of a cube. Even one step of a delta ball, doesn't matter how small you make delta, you're going to step out all the time. So how do you deal with this? So the solution is to start with this warm start. But in analysis, it's even more complicated, even analyzing the warm start. So what's actually done is that you consider what's called the speedy walk, where rather than doing rejection sampling, when you pick from the ball and go only if you're inside, you pick from the intersection of the ball with the set. It's only a theoretical tool, right? Because that itself is a general sampling problem, picking from the intersection of a ball with an arbitrary convex body. So the steps are proper nevertheless. How to implement is a question. So in fact, the implementation is by rejection sampling. It sounds like a little bit circular. But the point is that once you take this abstraction of taking a proper step, now it's possible to show that the conductance is just large period for every subset. And now all that remains is to analyze how many steps do you waste, and that you can bound when you have a warm start. So that's basically the very rough outline of the analysis. And that leaves us to the question of how to generate a warm start. That's an important problem that needs to be considered for this case. Yeah. Okay. So this progress on sampling has been over, as I mentioned, many different iterations, lots of interesting ideas here. And the one comment I want to make is the output guarantee in all these cases so far has been in total variation distance. So the total variation distance of the distribution of the point you output with the target is epsilon. Okay. Now we mentioned briefly the connection with functional inequalities. So a little bit more detail. Poincare inequality is for a distribution. So this is for an inequality for a target distribution pi. Is the following statement that for any smooth function, the variance of the function, right, over this distribution is bounded by this constant called the Poincare constant times the expectation of the squared norm of the gradient. If you can do this for any function, then that's the whatever constant you can do it with is the Poincare constant. In the case of log concave distributions, this can be reinterpreted entirely geometrically up to constant factors, both upper and it's tight up to constant factors, and it looks like this. So if you have a log concave distribution, it's asking for the inverse of the minimum possible ratio between the boundary and the volume of the set. The measure of the boundary and the measure of the set itself. Whatever is that minimum possible, the inverse of that is the Poincare constant up to absolute constant factor, 4. And then we know now that the Poincare constant is in fact bounded in terms of something much more concrete, the operative norm of whatever is the covariance matrix times log n. The conjecture is that this log n is just a constant. So that's it. A different inequality, stronger functional inequality, is the log sub log inequality, where you get a very similar form. The right hand side is the same. The left hand side, we're replacing variance with the entropy of f squared, which in general can be higher. So the log sub log constant is always more than the Poincare constant. Okay, so these are functional constants that are general and control the convergence of Markov kernels. Okay, so with that background, let me now mention the starting point of the main idea. So diffusion refers to probability distribution changing in continuous time. You're making some local change, but it's in continuous space and time now. So if you consider optimization, of course you can think of optimization as solving a differential equation, at least if you're going to a local minimum or a local maximum. So that's gradient descent. V is the function you're trying to minimize, the convex functions typically. And sampling, well, you can do a little bit more, but not much more. All you do is, in continuous time, you add a Brownian motion. So if you're not familiar with Brownian motion after time t is the same as sampling from a Gaussian distribution with variance t. But the point is you can actually think of it as a continuous process and build it up so that for any time t it gives you it's a non-trivial theorem to show that this construction exists, but it does. So now if you do this diffusion here, start at time 0 and run this for some convex function, or actually you don't even need convex, you need something milder than that, you'll end up with the target. In the limit, you'll reach the density that's proportional to the minus 2. So you've got this, that's our goal, right, to sample from this. You need access to the gradient, sure, okay, that's some little bit more maybe, But once you have that, at least in continuous time, there's your algorithm. Just solve this equation. Okay. There is a more very nice abstract connection between optimization and sampling. In particular, yes, sorry.
So this ground function, it comes to fix some noise?
I mean, it's just, yeah, you can think of it as infinitesimal Gaussian noise. Right, so we have to introduce some randomness because we're producing a distribution. And so even doing the simplest possible thing is independent Gaussian noise at every continuous time step, infinitesimal time step is enough.
Okay.
Yeah. So this is the high-level statement that was formulated in this paper by Jordan, Kindler, and Otto, and really cleanly made concrete by Vibisono. It says that sampling by Langevin diffusion by this continuous method, it's not an algorithm, is the same as optimization, where if you think of the space of measures, so every point is a measure, and the metric you're putting on measures is what's called the Wasserstein metric, so it's some metric, looks like Euclidean metric, you can think. And then the objective is the KL divergence, the relative entropy of your current point to the target. So you're trying to minimize that. So if you think of it like this, then in fact, this is gradient descent in this space. That's the simplest version of gradient descent. KL divergence, just in case, is just the expectation of the log of the ratios, or if you like, the integral of rho log rho over there. Okay.
So if one could discretize the diffusion, does that not also give a third?
Yeah, I mean that's the key question. So can you turn this into an algorithm by discretizing, right? So this is something, of course, people want to do in differential equations more generally, both deterministic and stochastic, and there is a whole field. But depending on how you discretize, there are errors that build up, yes. So that's the question: can we do this effectively to get polynomial time algorithms? So that's the thing. So but before we do that, one small step before that, what's the rate of convergence? Is this, what time? How long do I have to go for to reach this target distance? If I have to go for a long time, even in continuous time, maybe it's not such a great idea. But it turns out that you get exponential convergence. The rate of convergence is e to the minus t, and then this constant is determined by this log Sobolev constant. And note that the convergence is in the KL divergence, which is a stronger metric than the total variation distance. So if your target density has some log Sobolev constant, you're going to converge basically exponentially in multiples of that. I was going to put up a quick proof of that, but I think it's a good exercise in how to take the derivative of a distribution. But that's how it is. Yeah? Okay. So so then that leads to the question: how about an algorithm? This is basically the proof, and yeah, there are two elements in the proof. One is the definition of the log Sobolev constant. That's that inequality there. And the second one is the fact that whenever you have a differential equation like this, a stochastic differential equation, there is a corresponding equation that tells you how the distribution at time t is changing. So you use these together, and that gives you the convergence proof. Now, how about an algorithm? Okay. So here's the simplest possible discretization. Rather than taking infinitesimal time, let's take some finite time h. We'll make h small enough. So we're subtracting, right? The change was supposed to be the gradient, proportion of the gradient, and then here we're adding Brownian motion of variance time, right? So really it should be square root h times the standard Gaussian. Okay, that's the natural. So as h goes to 0, this will recover the equation that we wrote. And so what we showed in 2019 is that if we need an additional assumption on f, f is v, I'm sorry, the convex function, that if its gradient is bounded, so the function itself is L smooth, then you get this guarantee. So this is saying that the KL divergence of the k step, this is after k discrete steps like that, each with h as the step size, you get similar convergence. You see this part is very similar to continuous time, right? Because in continuous time you've done h times k time. but you get this error, which is quadratic in the Lipschitz constant, in the dimension, and in the log Sobolev constant times h. So of course now you can play a trick, right, where you make the h small enough so that this becomes smaller than any target epsilon, and you still make progress here. And that's what you can do. So basically, if you set h to be any target delta over this polynomial, then after this many steps, so basically linear in dimension, quadratic in the Lipschitz constant, and inverse in the target error, you get this target error. Okay, so there's, sorry?
But you are working with like a fixed epsilon, unlike gradient descent, you're not changing it with
I mean, so in continuous time gradient descent, there's no step size really, right? You just, yeah, it's,
like gradient descent, again, these accelerated methods and all.
there are many variations possible.
Yeah.
Indeed, there's a whole family of variations here. In the general case, this is still what we know, but in special cases, people do take it. So for example, if it's strongly log concave or if it's something extra. So you might notice in this proof here, we actually don't even need convexity.
Okay.
There's no convexity needed. All you need is that the function has an LSI constant, whatever it is, and is L smooth. So you could have, take a Gaussian and then you make all these little bumps in it. It's fine. Yeah. Yeah, it's been extended to other isoperimetric constants, things that are smaller than LSI. And there are better bounds for many special cases with more specialized algorithms. Okay. But the point is that you do need this L here, which makes it not a polynomial time algorithm for, let's say, uniform sampling or for log concave sampling. If I'm interested in, I really want a polynomial time in the dimension and the input specification. And you need the smoothness. So everything has been in TV distance. How about stronger notions such as KL, which do show up there naturally, or in even stronger, point-wise, I want the target distribution, the distribution I come up with and the ratio to be small everywhere, rather than just over there. That would be the strongest one. This is well motivated by applications, in particular by differential privacy, where they really need these stronger guarantees to go in there. Okay, so just to give you a picture, there are many notions of distances. We've talked about total variation distance here. There's this W2 distance. This is KL divergence, but you can keep going up. The Q Renyi divergence, and then the kind of the strongest is this, you're bounding the ratio between the densities everywhere. Okay. So, what is possible here in this picture and what can we achieve? So, there seems to be this gap, right? So, the classical literature in algorithm side gives you these metrics such as TV and chi-squared, uses conductance and speedy walk. And then there's the continuous-based analysis, which gives you stronger guarantees. We saw KL, but you can get RQ, and it's based on diffusion, and it uses a different set of tools, it seems. So is there a gap here? And the main point is that, in fact, we can bridge this, and we'll recover. I'll show you this new sampler. So there's at the heart of this, maybe that's the one idea. Actually, it's a simple new sampling algorithm. And you can get RQ and also R infinity. And the analysis will proceed using a continuous interpolation argument rather than conductance or more discrete argument. Yeah. Okay, so here's the sampler. I'll discuss it first for the special case of uniform sampling. Okay. Yeah. So this is your convex body. You want to sample uniformly. Let's say you're at the turn point x1. Each iteration is broken into two parts: a forward step and a backward step, whatever it isn't. So the forward step is just a Gaussian. At a point x, you pick a random point from a Gaussian of variance h to be determined, to be fixed. Okay. So of course, depending on where you are, it's quite possible that you'll step outside in one step. You may step outside. In fact, for a convex body, most of the points in high dimension, most of the points are near the boundary. It's quite likely you'll step outside. Okay, so you got there. That's the first step. The second step, backward, or you can call it snap back. You want to go back to the body, and you're going to sample again from a Gaussian of the same variance and centered at the point, except now you will only accept conditional on the point being in the set. Okay, so first step, just Gaussian, you always go. Second step, pick from a Gaussian, but only accept it if you land in the body. If you don't, you got to keep trying again.
So for this forward-backward phenomena, you don't no longer need the warm start.
We'll get there. Yeah. Yeah, no, we'll need it. We'll need it. But we'll be able to generate it efficiently. We will need it. Yeah.
Second step is rejection sample.
Yes, rejection sample. Yes. So Gaussian and then check if it's in the body. If it's not, try again. Try again means try from Y again. That's very important. You could have said try the whole thing again. That is basically the speedy walk. What does the speedy walk do? It's you start here, you pick from something around you, and you only accept if you're back in the body. That would be like saying do 2 steps and accept it, otherwise try again from the very beginning. Turns out that's very different from taking 1 step and trying from here to go back. Okay? Sounds like a little funny thing, but actually the distribution you get is different. In the case of what I'm describing here, the distribution this will give you is the uniform distribution. Or you'll see, in general, we can make it any target distribution. If I do speedy, the distribution is proportional to the volumes of these intersections. So things inside all have the same mass, but things near the boundary, depending on how close you are to the boundary, you get different distributions. Okay, so here's the algorithm. Sorry. You sample, so at a current point xi, you sample yi first, just by adding a Gaussian, and then you get back to the next xi point by sampling from a Gaussian again, but only accepting if it's in the set. Now how do you do that? Effectively, what we do is we try again, but we bound the number of attempts. It's crucial, it turns out. We'll fix this pattern. If you try more than a certain number of times, you'll declare the whole algorithm has failed and you restart the entire algorithm. Okay? You can't just go till if you just keep going till you succeed, then you can go off to infinity. Okay, so that's the algorithm. Now, what is this algorithm? Where is this coming from? Why this 2-step process and so on? It's easy to verify once I told you the algorithm that the distribution is correct and so on. But it's actually coming from what's called a proximal sampler. And that means that you're interested in the distribution on X, right? That was the distribution you're interested in. But I'm going to augment it with an additional point Y, again in n dimensions, so that the joint distribution looks like this. It looks like the original distribution times a Gaussian. Okay, so this is the joint distribution of xy. Now, this is what we're really sampling from. And if I look at just the x marginal, I get back the original, what I want. Okay? So the first step is resampling the y marginal, and the second step is resampling the x marginal. That's what we're doing. Okay. So in the analysis, which was previously done for smooth functions, derivational assumptions, in particular strongly log concave densities, what you can show is that you see there's this forward step where you're just adding Brownian motion, right? Because adding a Gaussian is just like adding Brownian motion up to a certain time. But then the backward step, which is the interesting one, is really exactly the time reversal of the forward step in terms of the differential equation. It's the time if I go for time t in the forward in the backward step, that's like going time h minus t in the forward step. So it's exactly the time reversal, and you can also write down a differential equation for that. So this is what happens here.
This is different from say coupling.
Completely different. Yes. Yeah. So because you do so, in fact, as a result, one can show that in both in the forward step, whether you use a Renyi distance or Taylor divergence, you actually get contraction in every step. In every step, your distributions are getting closer in your target distance, depending on the LSI constant or the Poincaré constant. If you only have Poincaré constant, it grows smaller in chi-squared. If you have LSI, it grows smaller in KL or Renyi divergence more generally. This is the forward step, right, where you're just adding Gaussian. That's believable, okay? But turns out the same thing also holds in the backward step. It would have been enough to show it doesn't get worse, but in fact it also contracts a little bit because it's the exact reversal of a Gaussian. So this what showed is that these contractions in the distances hold even when pi is not smooth. You don't need smoothness. You can have hard constraints. You can have non-smooth functions, and you still get this. And works for more general divergence. Okay, so last thing, maybe 2 minutes. How do I do this rejection sampling analysis? How do you know this is a finite algorithm? If you just do rejection sampling till you succeed in the second backward step, it will fail because the number of steps you need to take cancels with the probability of making the step, and you get infinity as your expectation. So we bound it, and here the idea is, and this is the first place we're using convexity. Everything in the contraction works very generally. There's nothing about convexity there. So here what we're saying here is that, first of all, we're choosing the h small enough so that your first step keeps you with high probability in a small shell, in a small expansion of the original set, a delta expansion. Okay. Now this is the effective domain, and as long as you're in that small shell, you don't need too many steps to come back in on average. That's the idea. So you can set this threshold up front. In fact, it doesn't even take that much. It takes much smaller than that, but you never exceed that threshold. So your overall expectation is small.
This is isoperiodic.
Sorry?
This is isoperiodic.
Yeah, so why is this, sorry, I'll thank you in a second. Why is convexity useful here? Because what we need here is that the ratio of the boundary to the volume of the set, the ratio of this expanded set, k delta to k, should be small. That shows up in it. We need the volume of k delta to k to be small. If your set is not convex, you can have a very large boundary compared to the volume, and then you take one small step, you may stay near in distance, but you really have a very little chance of coming back inside. Okay, so in fact, the analysis should work for any set for which the boundary is small compared to the boundary. Yeah, you don't really need convexity. Okay, so here's what you get as the final guarantee, that you recover the runtime of the ball walk, except now the analysis, it's really this walk, and the guarantee is in any Renyi distance divergence. And the warm start you can generate using just n squared r squared. Okay. This can be extended to general log concave densities. It will just be an in and out sampler. I don't have time for this. And so here's the status. Log concave sampling with and without a warm start and integration can be done in the same complexity as uniform sampling now. The previous methods where there was a gap between uniform and log concave. These algorithms for warm start generation and integration rely on extensions of Gaussian cooling, and the reason we're able to carry out this analysis in generality is because of the stronger Renyi infinity guarantees. Without these, this was not working. And also they lead to much cleaner analysis for the analysis of expectations and estimates when you have non-independent samples. So here are some open questions. What's the right answer here? I mean, it's an oracle model, so it is a good reason we should be able to figure out the right answer. There's no p equal to np issue here. We should be able to go way beyond log concave or convex settings. Can we hope to characterize at least when this method works? A question about hit and run, like we said, can we avoid the warm start penalty? So even the log m, maybe it should be log, or maybe just a polynomial independent of where you start. We don't know that. I mean, a small polynomial. We know n cubed from simple analysis. And here's sort of more of a probabilistic question. Suppose I start from a nice point like the center of gravity. At no warm start, I actually start from the point. Can you show that it converges in polytime? We don't know that. For the ball walk. For hit and run, we can show it no matter where you start. Finally, and this is probably my favorite question, can you deterministically estimate the volume of a polytope? Explicit polytope, ax less than or equal to b. I give you all the inequalities. Give me an estimate of the volume within a factor of 2. Okay. There's no lower bound in off. Yeah. So, thank you.
Possible application of this in approximation algorithm or distributed like Lovett method had impact.
That's an interesting idea, yeah, because we do get stronger guarantees on the distribution on the way. Yeah, I hadn't thought about it, but yeah.
Thanks for one more question.
So in the
Okay, welcome back. Next we have John Hershberger as our next speaker. He is a principal engineer at Mentor Graphics, and he obtained his PhD from Stanford University. Then he worked as a member of technical staff at the Digital Equipment Corporation Systems Research Center, and after that he moved to Mentor Graphics in 1993. He made several contributions to computational geometry. One of his biggest breakthrough results, along with Subhash Shuri, is to compute a shortest path with polygonal obstacles in n-log n time, which settled a big open problem then. He also introduced kinetic data structures and studied them extensively. For his contributions to geometric computing and designing tools for integrated circuits, he was named as a ACM Fellow in 2012. Today he will be talking about snap rounding. So let's welcome John.
Thank you very much for the kind introduction, and thank you to the organizers for inviting me. It's been a wonderful workshop up to now. So, as we get started, I want to lower your expectations immediately. This is not a talk about theory, at least mostly, except around the edges. It's not a talk about experimental comparison of different algorithms. It's not about approximation, except tangentially insofar as rounding is an approximation of a real valued result. What it is about is implementation, my experience with implementation. And it's about theory and practice and the relationship between them, which is sometimes perhaps adversarial, or so it seems. That it's an alternation of success and failure. The setting for this work is integrated circuit design and verification, in particular a software product called Calibre that I've been working on for 17 years now, I guess. It's a system for the design and verification of integrated circuits. It was developed by Mentor Graphics, which is now part of the much bigger corporation Siemens. And Calibre is used to verify basically all of the chips that are manufactured in the world. The particular problem that I'm talking about is a useful subroutine in the design in the verification system, polygon Boolean operations. For these operations, the inputs are layers of metal, polysilicon, diffusion, the different things that make up an integrated circuit, and you want to do some operation on those inputs. For example, if you've been provided a set of polygons as input, you want to reduce those to a single layer for the manufacturing process, and that's called a single layer OR operation. Or if you have two different layers, say polysilicon and diffusion, you might want to find the intersection between those because those are the gates of your integrated circuits, your MOS devices, and so on and so forth. And I have a couple of examples at the bottom of the slide. Now this is a classical computational geometry problem with a classical computational geometry solution. You overlay the subdivisions that are induced by the input polygons, and you select the regions of the overlay based on the coverage, oftentimes just the depth of coverage, the winding number of the regions. And typically you would implement this with plane sweep, and in the computational geometry world, this would be described as running on the real RAM, but unfortunately, the real RAM doesn't work in the real world. What we have is, we need to do some rounding. So the edges of the input are a collection of line segments whose endpoints are on the integer grid. When we compute the intersections of these line segments, those intersections will oftentimes not be on the integer grid, but we want the output to be represented with integer grid points. So that means that we need to round the intersections to the integer grid points. Now, this is all pretty simple stuff. No big surprises here. Pixels are defined to be unit squares that are centered on the integer grid points. And if two line segments intersect inside a pixel, then we just want to move the intersection to the pixel center, which would then break the segments into polylines, polygonal paths. However, this simple idea does have some subtleties. If you just round the intersecting segments without paying attention to the environment around them, then you may invalidate the topology of the arrangement. So on the left-hand side, this vertex up between the green edges gets snapped to the center of the pixel, and it reverses the orientation of the triangle, which is going to cause big problems downstream. You don't want to do that. There's another methodology issue, I guess, that isn't necessarily obvious. When I started work on this problem, which was all the way back in 2007, there was already a rounding algorithm in use. And that algorithm used a sweep line, and it rounded the segments during the sweep, so that the right-hand side of each rounded segment was subject to future rounding. And the problem with that is that error can accumulate. With the result that the final perturbed polyline could end up being arbitrarily far from the original input segment. Now, it's true, that doesn't happen very often. It sort of takes adversarial input for it to occur, but it is possible, and you'd have to worry about that. So at the time that I did the implementation, I was a big fan of snap rounding, and I guess I still am a big fan of snap rounding. So I decided to use it as the basis for my polygon Boolean operations. So let me tell you about snap rounding. Snap rounding is really simple. It was invented by John Hobby and Dan Green back in the 20th century, and it's a simple method, simple to describe, that preserves both topology and accuracy in the rounded arrangement. So the whole definition is here on the slide. Any pixel that contains an intersection of two original segments or an endpoint of an original segment is defined to be hot, a hot pixel. Then any original segment that touches a hot pixel will be deformed to pass through the center of those hot pixels. And so each original segment is replaced by a polygonal path joining the centers of the hot pixels intersected by the original segment. And that means then that each edge of the rounded arrangement represents one or more deformed segments. So here at the bottom of the slide is an example showing the effect of snap rounding, where the squares are the hot pixels, and on the right-hand side we have the rounded arrangement corresponding to the input arrangement. As I said, snap rounding guarantees accuracy, and it guarantees maintenance of topology. Accuracy, the rounded result of an original segment lies within half a pixel distance of the original input segment, which is pretty obvious because the replacement for an input segment is just a polyline joining the centers of the hot pixels that the original segment touches, and all of those centers are within half a pixel of the original segment, and so the line segments joining those centers are also within that half pixel distance. Secondly, I have to be careful about topology, about what I mean by topology, but here I mean ordering and adjacency relationships between segments and faces. In particular, the order of intersections of segments are preserved and the orientations of triangles are preserved up to collapsing of features, which is an important distinction to make. the proof that topology is preserved is due to Gibas and Maremont. And I will need it tangentially later, so I'm going to describe it in a little bit of detail here. So the idea is that you break the original segments at the places where they cross the hot pixel boundaries. And then, that is, each segment is broken at its first and last intersection with the hot pixel boundaries that it touches. And then you shrink the hot pixels to their centers uniformly, first by a uniform horizontal contraction and then by a uniform vertical contraction. And that means that the arrangement inside the hot pixel as it shrinks uniformly along with the pixels, so all the topological relationships inside the pixel are preserved. The segments that are outside the hot pixels are just dragged along by the endpoints. They remain straight line segments being dragged along by the endpoints. And the key observation is that for topology to be invalidated, a subsegment that starts outside of the hot pixels would have to cross into a hot pixel, because inside the hot pixel is where the endpoints and the triangle vertices lie. But when the segment is being transformed, its endpoints, let's look at the horizontal compression first. The endpoints of the segment are contracting toward the centers of the hot pixel, and so the endpoints are moving either left or right at a speed of at most 1. If the pixels are contracting with speed 1, then the endpoints are moving with speed at most 1. 1 if they're on the vertical sides, less than 1 if they're on the top and bottom of the hot pixel. And since every point on this line segment is a convex combination of the endpoints, then that means that each of those internal segments is moving left or right with a speed of at most 1. And since the corners of the hot pixels are contracting inward at speed exactly 1, anything that starts outside can never cross to inside. Okay, now I want to change gears a little bit and talk about implementation. I wanted to build a library of components that could be used to implement many applications, not just polygon booleans. So I wanted to separate the geometry from the functionality that used that geometry. And to do that, I implemented a Bentley-Ottman scanline, and I used C++ templates to define 6 policies. An input policy extracts the edges from compressed storage and presents them to the scanline in left to right order. The scanline representation holds the edges that cross the current X position in bottom to top order. The rounding policy uses that scanline representation to determine the hot pixels and the rounded subsegments. A region characteristic, which we'll come back to later, maintains some application-specific characterization of the region above each edge. And an output policy receives rounded edges from the rounding policy. It consults the scanline representation and the region characteristic to produce some application-specific result. And finally, an event manager ties all of this together. It passes messages between these different components, and it updates the region characteristic only where it's necessary. So, okay, this is all very abstract. Let's talk about implementation of the Boolean operations, how it fits into this framework. We only need to customize 2 policies, namely the region characteristic and the output policy. In this case, the region characteristic is going to compute the winding number of each region in the winding number above each edge in the scanline. And it does that essentially by computing a sum from bottom to top with +1 for bottom edges and -1 for top edges, except that it's going to be updated only in the places where the value changes. And then the output policy is going to identify edges that belong to the result of the Boolean operation. So for example, for an OR operation, if the winding number is greater than 0, then you're inside the result. If the winding number is 0, you're outside the result, and edges on the boundary between those need to be sent to the output. So that was the general shape of the implementation, and the result was good performance and predictable output. Yes, question?
So, I mean, you roughly break each segment into n segments, right? If it intersects every other line.
In the worst case, yes.
So, does that mean that the algorithm now runs much slower than if you were just running it with the real RAM model and all of that?
It's not slower than if you were running it with the real RAM, no. But it is true that the runtime is dependent on the complexity of the input, and there are algorithms, some of which I've developed, that can be more efficient, that are output sensitive, that don't necessarily have to look at the full complexity of the input arrangement. But as it turns out, in the application, the integrated circuit design application, that doesn't happen. And a lot of implementation and for real applications is driven by what shows up in practice. Yes?
What about number types? There is a certainty in the computation whether a line segment passes through a hot pixel.
Mhm.
Is your implementation complete in this sense? You use floating point numbers or you use exact numbers?
Excellent question. I was hoping to sidestep that. But I use floating point and I use essentially multiple precision when necessary. So it's a, what is the right word for it? It computes the answer with an error bound. If the error bound is good enough, which it generally is, then we know what the answer is and we don't have to do any more refined computation. So floating point is good enough most of the time, and that's good enough. But when we cannot prove that floating point is good enough, then we do a computation that uses some integer arithmetic and GCDs and stuff like that.
So you take care of this?
Yeah. Yeah. And the algorithm that came before did not. And that caused problems. That was one of the reasons that I got into this business in the first place.
John, so when you collapse a triangle, I understand if you collapse an edge, it's okay maybe in application, but collapsing a triangle really can change things. So does it not cause any problem in the practice?
If a region that is, there are cases where collapsing a triangle can change the connectivity of things, and this can be a problem. Code has to deal with it somehow. It was going to happen anyway. But
I would just add that you know everything. So in the output, you can warn the user in the next step exactly what happens in this collapse. You don't lose any information.
that is true.
Even down the line, like one collapse can trigger other?
No, the collapses are independent.
Oh,
There's no interdependence here.
Anyway, moving on. So as this new implementation became more widely adopted, differences from the old method began to be noticed. So here's one example. Hot pixels are closed on the left and bottom sides and open on the right and top sides. which means that rounding is, in fact, it has to be asymmetric. So in this example here on the left-hand side, the outer diamond, only one of those 4 segments touches the hot pixels determined by the inner square. In particular, the lower left one touches that hot pixel, and so the rounded arrangement is asymmetric, as shown on the right. And how you respond to that depends on where you come from. My inclination was to say, yeah, so that's the way it is. But our software testers had a different response. And they tended to say, this algorithm is worse on this example than the previous code. And I want an algorithm that does the right thing on all of my test cases. And, you know, it's somebody like me can climb up in my ivory tower and say, this kind of undisciplined wishing for a simultaneous solution to incompatible requirements is how we ended up in this mess. But it's a hard sell. And I started to wonder whether maybe there could be a better rounding algorithm that would make everybody happy. And I first thought of stable snap rounding, which I invented about 15 years ago to try to make snap rounding idempotent. And the idea of stable snap rounding is that it splits snap rounding's hot pixels into 2 classes, magnets and pins, depending on the location of the arrangement vertices. So magnets contain at least one non-integral arrangement vertex, and pins contain exactly one arrangement vertex at the pixel center. And in stable snap rounding, a segment is forced to go through the centers of the magnets it contacts, but it's only constrained not to pass over pins. So in this example, the dashed segment is our input segment. It contacts magnets at the left and right, and it passes through a channel between the pins, and as it snaps to the centers of the magnets, it wraps around the pins, but it is not required to touch every single pin. So here in this example, the bottom left segment is not forced to pass through the pin in the bottom center, which means that the rounded arrangement shown on the right is different from the way it would be under standard snap rounding, comparing these two. And that means that on the problem test case that we had before, we get the desired behavior. We get a symmetric result from a symmetric input. So stable snap rounding would fix the asymmetry, but it would also change a whole bunch of test results. And I had been through a long qualification process, and I really didn't want to do that again. So I rejected stable snap rounding. Instead, I wanted something small and simple that would fix the asymmetry, and it wouldn't break anything else. So I thought of something that I called relaxed snap rounding, which is like ordinary snap rounding, but it borrows one small idea from stable snap rounding. And the idea is that if a hot pixel contains no original segment intersection, and it has segment endpoints only at its center, which is basically the same as a pin in stable snap rounding, then a segment that crosses the lower left corner is not considered to contact that hot pixel. Very small change.
This sounds dangerous.
I wish I had had you sitting next to me at the time that I thought of this. But this gives the desired behavior on the example that was the problem. And we can prove that it has the same good behavior as ordinary snap rounding. The proofs basically carry through unchanged. So, hooray! I was actually quite pleased with myself. And I even considered whether this tweak was worth writing up as a small but useful enhancement to snap rounding. So, let's enjoy the moment. But, unfortunately, a year later, people started to notice that the polygon Boolean operations sometimes produced results that weren't well formed, like this weakly simple polygon. So the system is saying that these two polygons are a single polygon joined by edges that actually happen to be coincident. And I didn't understand why this was, and it took several days of debugging before I figured out that there was a crucial weakness in this relaxed snap rounding scheme, which is that no snapping means no noticing. So in this example, we want to compute the and of the two polygons on the left. And there are three hot pixels that matter here. Two of them caused by intersections, and one of them caused by a vertex at the center of the hot pixel, that's pixel B. And so the segment AC that passes through the lower left corner of pixel B doesn't notice it, is not snapped to the center of B. But snapping in the first and third pixels causes the segment AC to be pulled into contact with the center of pixel B, and that splits the results into two pieces. On the other hand, if that third hot pixel doesn't exist, then the segment AC doesn't deform as much, and the result doesn't pinch off. You get only one polygon instead of two. And the crucial problem is that at the time of processing pixel B, we can't know what the future holds. We can't know whether it's this case, no pinch off, or this case, yes pinch off. So, what to do? At this point, relaxed snap rounding seemed like a terrible idea to me, and I wished I could go back, but there was a year's worth of water that had flowed under the bridge, and people had gotten used to the better behavior in the cases when it did give better behavior. So I couldn't just back it out. So, how to find and fix those previously undetected incidences? So at this point, it was time to put on the theory hat and try to characterize where those incidences can occur. So suppose that you have this situation where there's an original segment S and a hot pixel H that have an undetected incidence. First thing, we can argue that the segment extends to the left and to the right of the hot pixel H. S has to move up and to the right to hit the center of H. So that means that S has to snap up and to the right by 1/2 in the hot pixels that it contacts before and after H. That is, S is passing through the lower left corner of those pixels before and after H. So therefore, those hot pixels have to be to the left and to the right of H. Secondly, other segments don't enter H through the bottom, because if they did, that would create a hot pixel for S in the column below H, and therefore S would not be able to snap up into the center of H. Third, the triangle that is below H and above S is empty of any other segments except for possibly those that came passing through H. because any segment that intersected that triangle would create a hot pixel for S that is not to the right of H. So that means that S is the first segment below the bottom segment in H, either on the left-hand side or on the right-hand side, which means that hot pixels that might have a possible undetected incidence can be detected in constant time, no extra cost asymptotically. And so that, oops, I turned my notes one page too far. So this characterization gives us enough of a foothold that we can fix the problem. So we define a vulnerable vertex to be a hot pixel that has an original segment passing through its lower left corner. And as we just saw, we can detect those in constant time per hot pixel. Then we maintain a sliding window of vulnerable vertices. And whenever we encounter a segment that snaps up and to the right by 1/2, then we check whether it hits a vulnerable vertex. And if it does, we extract the edges of any polygon that touches that incidence. And because the edges belonging to the same polygon are maintained in a union-fine data structure, it's actually possible to identify all of the edges that belong to those polygons. So we extract those edges and we perform another OR operation without snapping on the extracted polygon edges, then renumber the polygons and integrate them back into the original, into the result. And this, the OR operation, this may cause some edges may annihilate, some polygon interiors may pinch off and become two separate polygons. We detect that in the process so that we end up with correct results. Whew. Success? Well, sort of. I would say it's really a tie at best. The implementation is more complicated than I would like, and some of the benefits of the scanline methodology got lost. But there are other problems to solve. Declare victory, move on. So this is the point where we do summaries and lessons learned, and I guess this is kind of an obvious thing, actually. Just implementation is hard. There are hidden dependencies, the requirements are murky, you figure stuff out too late. But if you are able to combine theory with implementation, then there are extra challenges, but there are also better results. I guess another question is lessons learned. Have I learned my lesson? And for good or for ill, no, the answer is no. I'm still working, actually just playing at the boundary between practice and theory, trying to find interesting theory that can apply to practical problems, trying to find practical problems where theory can make a difference, and trying to implement efficient, elegant solutions to real-world problems. It's a good life. That's all.
Questions?
Yeah, Mark.
I was a bit wondering about the last example that you gave. To what extent that was actually the wrong answer that you first got? I mean, okay, you have this thin sliver, but somehow that also seems to be, inherent to rounding. And in actual fact, it was one polygon, right, that you were trying to compute, or was I missing something there?
You're speaking of
Exactly.
That one.
That one. Why is this the wrong answer? What should the right answer be?
The right answer should be polygon 1, polygon 2. Because the definition that we use for polygon is interior connected.
So what happens if you have a polygon that vanishes because it's very thin and it collapses to a segment and it just disappears? Or?
It just disappears. and this is something that you have to cope with. And because the output requirement is that the output is integer vertices, sometimes polygons are going to disappear. And that means that the software that deals with them is going to have to cope with the possibility of polygons disappearing. And I can tell you a whole other war story about things like that.
Because here I was thinking that you don't want them to disappear, but you just accept that they have zero width. But apparently that's not what people want.
Yeah. Yeah, because electrically connected is what a polygon means, really.
Electrically connected.
Yeah.
So, did you try to extend it to curved objects?
To
Curved objects?
a whole nother story. This is if I was thinking of. I'm thinking about it, talking about that in the open problem session, because that is a very active area of work right now,
Yes.
trying to support spline objects with some kind of Boolean operations, and we have a partial solution that is okay, but it is not as good as I would like. So there's all sorts of interesting stuff to do there.
Thank you.
Yeah, Danny.
Please don't misconstrue my question as provocative. But I'm really curious, have you considered that there is Boolean operations and snap rounding in Siga? Have you considered using it, or did you reject it for some reason?
Mostly, the caliber system is I considered it. Yes, let me start with yes, I considered it. The translation from the internal formats into Seagal and back was the thing that concerned me. Yeah, Anna.
Can you briefly explain again where the original asymmetry of snap rounding comes from? Because snap rounding looks very symmetric to me, so I missed something in the example you gave where it became asymmetric. And then your solution was also asymmetric. Yeah, why is it doing that? I mean,
It's because every hot pixel, every point in the plane belongs to a hot pixel. So then the question is, what about the points on the edges? And the definition is that the left side and the bottom are closed, the right side and the top are open because they belong to somebody else. And that means that the lower left corner belongs to this hot pixel and to nobody else.
okay.
And so that point right there belongs to this hot pixel, but that point, and that point do not belong to these.
Okay, thank you.
And truth be told, there is asymmetry. You can't avoid asymmetry. It's just that in this particular case, it was very much a challenge-driven response.
Because you cannot snap to two places, so you have to decide.
Yeah.
Yeah.
Yeah, Tamal.
So, in one of my very distant life, I considered a challenging problem of computing Boolean operations on polyhedra. And I gave up. I did not, I could not succeed. But did you ever consider polyhedra with this technique, the computing Boolean operations?
I have thought about like snap rounding for polyhedra, and it seems too hard.
Right, nothing wrong.
There are results now, but
Yeah, it's
insane.
Thanks, John, again.